Hi there. In this video I'll be answering a question about Millikan's oil drop experiment, calculating the charge on the oil drop and discussing the idea of quantization of charge. Here's the question from the 2007 Old Advanced Higher paper. You'll notice that I'm only answering part of the question, as parts A and B don't relate to Millikan's oil drop experiment. The question says, a charged oil drop of mass 1.2 times 10 to the negative 14 kilograms is stationary between two horizontal parallel plates. There's a potential difference of 4.9 kilovolts between the parallel plates. The plates are 80 millimeters apart, as shown in figure 7. We're then asked to draw a label diagram to show the forces acting on the oil drop. So, if we look more closely at the oil drop, it would of course experience a weight force downwards. The other force acting on it would be an electrical force which acts upwards. Notice that the top plate is attached to the positive terminal of the power supply and the bottom plate to the negative terminal. There would of course be a uniform electric field between the plates, and the oil drop, which is always negatively charged, experiences an electrical or electric force because of this. The size of this force is varied by altering the potential difference between the plates. So this is how we could draw our diagram. Just remember that the forces are balanced, so the lines should be of the same length. C part 2 asks us to calculate the charge on the oil drop. So the weight force can be calculated using this equation. W is equal to mg, where m is the mass of the oil drop and g is the gravitational field strength, 9.8 newtons per kilogram on Earth. The electrical force can be calculated using this equation. F is equal to QE, where Q is the charge on the oil drop, what we're trying to find, and E is the electrical field strength between the plates. Since the oil drop is stationary, the forces acting on it are balanced, so the magnitude of these two forces is the same. The electric field strength between the plates can be calculated using this equation, where V is the potential difference between the plates, 4.9 kilovolts, and D is the distance between them, 80 millimeters. If we substitute the second equation into the first, we get this. QV divided by D is equal to mg. We can then make charge Q the subject of the equation by dividing both sides by V over D. This is the same as multiplying by D over V. So the equation becomes Q is equal to mgd divided by V. We can then substitute our values into this equation, remembering to convert distance to meters and potential difference to volts. This gives us a final answer of 1.92 times 10 to the negative 18 coulombs. Part 3 of the question asks us, how many excess electrons are on the oil drop? To answer this, all we have to do is divide the charge on the oil drop by the charge on a single electron, 1.6 times 10 to the negative 19 coulombs, as found in the datasheet. This gives an answer of 12 electrons. Of course, the charge on the electron is actually negative, meaning that the charge on the oil drop would also be negative, since it picks up excess electrons. To answer this question though, we only need to consider the magnitude of the charges. When Robert Millikan carried out this experiment, which now bears his name, he found that the charge on any oil drop was always equal to an integer multiple of a certain value, which he proposed to be the charge of a single electron. This is because the oil drop, or any object for that matter, can only gain or lose a whole number of electrons, so charge is therefore quantized. The charge on an object can only be equal to an integer multiple of what's called the fundamental charge, the charge of an electron or proton. Part D of the question relates to this. The results of Millikan's oil drop experiment led to the idea of quantization of charge. A down quark has a charge of negative 5.3 times 10 to the negative 20 coulombs. Explain how this may conflict with Millikan's conclusion. So again, we divide the magnitude of this charge by the charge on a single electron, but this time we don't get an integer multiple of 1.6 times 10 to the negative 19 coulombs. So we could write this as our answer. Quarks have what's known as fractional charge, the charge of the down quark being equal to 1/3 of the charge of an electron, although quarks can't exist as isolated particles. If you're interested in finding out more about this, then look up quark confinement, although it goes beyond what we need to know at advanced higher level. And that, I'm afraid, is the end of the video. For more information on upcoming videos, summary sheets and so on, visit physics-podcast.co.uk. Thank you for listening.